Previously, we have focused exclusively on the situations where there is only one population. We have discussed the statistical techniques for estimating and testing for population mean and the population proportion for one population. In this presentation, we would discuss the statistical methods for estimating and testing for population proportion for two populations. These techniques are quite similar to what we have discussed before, and the challenges lie in the distinguishing two populations from one population. The kind of data for dealing with population proportions is generally categorical data. There are largely four types of questions for analyzing categorical data. The first type is on the sampling distribution of sample proportion P bar. The second one is to compare the population proportion P with some threshold constant P0. We have already discussed these first two types of questions in previous videos. The third type, that's also the one which we would address in this video, is to compare proportions from two populations, P with subscript 1 and P with subscript 2. The last type of questions would be discussed in later videos. Questions for either categorical data or numerical data can be largely divided into two groups, estimation versus hypothesis testing questions. I've summarized all the formulas for estimation and hypothesis testing questions for both categorical data and numerical data in a table format. This formula table can be found on our course website. For categorical data, let's take a look at the estimation problems first. This table summarized the formulas involving one and two populations. In estimation questions, we are generally asked to develop a confidence interval. As we have discussed in previous videos, for one population case, the confidence interval is equal to a point estimate, typically the sample proportion P bar, plus minus a margin of error. The margin of error is the product of a multiplier, which would be a z multiplier here, and the standard error. For hypothesis testing questions, what we usually do is to compare the population proportion P with a threshold value, that is a constant number, typically given in the question, and we call it the null value or P0. To carry out a hypothesis test, we would have to find a test statistic which can be computed using the difference between the evidence and the null value and divided by the standard error. The resulting test statistic is a z-score. We would then complete the rest of the test by looking up the corresponding p-value or the critical value for the test before we are able to make a conclusion. Let's work on example 1 first to see how this formula table can be easily used to solve estimation and hypothesis testing questions. A new soft drink is being market tested. A sample of 400 individuals participate in the taste test, and 120 indicated they like the taste. Part A. Carry out a hypothesis test to see whether more than 21% of the population will like this new soft drink. Assume 5% significance level. Part B. Estimate the true proportion of population who will like this new drink at 95% confidence level. The variable of interest here is whether an individual likes this new drink or not. So it's categorical data. This means we would be working with proportions, measuring the proportions of individuals who like the taste. The wordings of Part A indicate that this part is a hypothesis question, whereas Part B is an estimation question. We will use the formula table to solve them separately. Before we begin with the 4-step procedure for solving hypothesis testing questions, we would summarize the numerical information from this story problem. The sample size n is 400, as there are 400 individuals participating in the test. Out of the 400, there are 120 who like the taste. The sample proportion of individuals who like the taste is 120 over 400. We would compare the population proportion P with 21%. so 21% is a constant threshold that is also the P0. P0 is 0.21. Now we would start with step 1. To see whether more than 21% of the population will like this new drink, we would set up this as an upper-tailed test. More specifically, the alternative is P is more than 0.21. So the null is P is less than or equal to 0.21, where the alternative is P is greater than 0.21. Step 2 involves computing a test statistic, and this would be a z-score. I'm using the formula given on the formula table. Because we have already found the sample proportion p bar and a threshold p0, sample size n, we can easily plug these numbers into the formula and obtain a test statistic of 4.42. For an upper-tailed test like ours, the critical value is a positive value with an upper-tailed probability equal to the significance level of 5%. This critical value can be found to be 1.645 using the z-table. The center of this bell curve is where the null value is. The center also corresponds to a z-score of 0. Compared to the critical value of 1.645 which we just found, our test statistic 4.42 is further away from the null value. This means we have sufficient evidence to reject the null at the 5% significance level. Similarly, we can solve this problem using the p-value approach. Instead of finding the critical value, we would need to compute a p-value, a probability instead. For this upper-tailed test, p-value is the upper-tailed probability of our test statistic 4.42. That is the probability to the right of 4.42. The largest z-score on the z-table is 3.09, which has an upper-tailed probability of 1 minus 0.999, that is 0.001, a very small probability close to 0. Our test statistic 4.42 is even larger than 3.09, suggesting that the upper-tailed probability of 4.42 should be even closer to 0. That is essentially 0. We reject the null hypothesis when the p-value is smaller than significance level. In conclusion, we reject the null statement and conclude the p, the population proportion, is indeed bigger than 21%. That is, there is more than 21% of the population who will like this new drink. Now we move on to part B. We would like to construct a 95% confidence interval for the population proportion P. The first step is to find a point estimate. That would just be the sample proportion P bar. That is found to be 0.30. The formula is given on the formula table. It's under the estimation and for one population case. I copied the formula here. The standard error part is easy to find. That is just plugging p bar and sample size into the square root formula. The slightly more challenging part is to figure out the multiplier. For categorical data, this would always be a z-multiplier, just like the test statistic for part A is a z-score. The confidence level is given to be 95% in the question. Using the z-table, we look for the middle area to be 95%. The two corners on the two ends would be 5% in total. Each corner is 2.5%. The z-multiplier is the positive z-score with an upper tail of 2.5%, that is 0.025. Looking this up, this z-multiplier is 1.96. This is also one of the three magical numbers we have discussed when we first talked about confidence interval a few videos ago. The other two magical numbers are 1.645 and 2.575 respectively. With 1.96 plugged into the formula, we find the 95% confidence interval to be 0.255 and 0.345. That means we are 95% confident the population proportion who like the new drink is between 25.5% and 34.5%. I hope you agree with me that using the formula table, we can easily solve questions either estimation or hypothesis testing on population proportion for one population case. The same can also be said for two populations, as we will see next. For two populations, we would have population 1 and population 2 here, and their respective population proportions would be called P1 and P2. We are interested in comparing the population proportions, P1 versus P2, that is equivalent in finding the difference between the two population proportions, P1 minus P2. Finding a confidence interval for the difference of the population proportions is quite similar as before. We would need to find the difference of the sample proportions first and use that as the point estimate. The margin of error part is just a combination of the previous formula for one population case. For hypothesis testing questions, we would be interested in testing to see whether the difference between two population proportions is 0 or some other constant number. I call it D0. The formula is quite similar as the one population case, except that to find a standard error, we would need to find a p-bar first. The p-bar here is no longer the sample proportion as in the one population case. Instead, it will be the pooled proportion, which pulls the information from sample 1 and sample 2. I will use the following example to demonstrate how to solve estimation and hypothesis testing questions for two populations. Example 2. Winter visitors are extremely important to the economy of Florida. Hotel occupancy is an often reported measure of visitor volume and visitor activity. Hotel occupancy data for February in 2 consecutive years are as follows. There are two populations here, occupancy in 2017 and that in 2016. The variable of interest here is whether a room is occupied or not, so it's categorical data. We work with proportions, measuring the proportions of rooms that being occupied in those 2 years. When we work on the following questions, it is useful to identify the question type. Part A asks for the point estimate of change in proportions of room occupancy from 2016 to 2017. So it is an estimation problem. Part B asks for a confidence interval. So it's also an estimation problem. Part C asks to test whether there has been an increase in proportion of rooms occupied from 2016 to 2017. This is a hypothesis testing question. We would use the different statistical tools to solve these questions and with the help of a formula table. I would first summarize all the numerical information from this story problem, especially because we have two different populations now, we will have two sets of different numbers. I denote the year 2017 as my population 1 and the year 2016 as my population 2. You can use 2016 as your population 1 and 2017 as your population 2. It doesn't matter. You just have to be consistent in your calculations. Sample size 1 would be the number of total rooms in year 2017, that is 1,750. So N1 is 1,750. N2 would be 1,800. There would also be two sample proportions. P-bar 1 is 0.84 and P-bar 2 is 0.81. For part A, the point estimate of the change from 2016 to 2017 would be the sample proportion in 2017 minus the sample proportion in 2016. So that is P-bar 1 minus P-bar 2. That's going to be 0.03. This says there's a 3% increase from 2016 to 2017. For part B, we would be using the formula on the table to build a 95% confidence interval. Again, it is the point estimate which we just found in part A, that is 3% plus minus the margin of error. The multiplier here is a z multiplier right out from the z table. This part becomes easy because we have P-bar 1, P-bar 2, N1, and N2 ready. The z multiplier for 95% confidence level is 1.96. Plugging all these numbers into the formula, we get an interval of 0.5% to 5.5% for the change in population proportion from 2016 to 2017. For part C, we need to carry out a hypothesis test to see whether there has been an increase from 2016 to 2017. The research question here is going to be there is an increase from 2016 to 2017. So the alternative will be 2016 is higher than 2016. We used P1 to represent the proportion for 2017 and P2 for 2016. So the alternative will be P1 is higher than P2, and the null is the opposite of that. To be able to use the formula in the table, we would have to present the relationship between P1 and P2 in terms of their difference, that is P1 minus P2. We change the null and an alternative statements to their difference. P1 is more than P2 becomes P1 minus P2 is more than 0. To find the test statistic, we compute the pooled proportion to be 0.8248 first. This is actually the total percentage of occupied hotel rooms in these 2 years, about 82%. We call this pooled proportion P bar. Again, this is not a sample proportion. The sample proportions for the two populations are P bar 1 and P bar 2 respectively. Using the pooled proportion P bar 0.8248, we are able to calculate the test statistic to be a z-score of 2.35. I solved this problem using the p-value approach. We could also solve it using the critical value approach as well, and you should always get the same conclusion. I find the p-value to be the upper-tailed probability of the test statistic, which is 0.0094, smaller than the significance level of 5%. Therefore, we have enough evidence to reject the null and conclude P1 is indeed higher than P2. There has been an increase from 2016 to 2017 in terms of the proportion of occupied rooms.